Till now, we have talked about the combinational circuits, like we have talked about some logic gates and making circuit using them. Now we will move forward to the sequential circuits. So let's the sequential circuit. In the sequential circuit, we give the multiple inputs, and there will be and the output will also depend on the previous outputs. So you can see here we are feeding back the previous output using a feedback loop. So this path we say it as a feedback loop. So in the sequential circuits, it is the special type of circuits that has a series of inputs and the outputs. The output of the circuit also depend on the previous output of the circuit. So the main problem is why we need the sequential circuit. We already have the combinational circuit we have gone through. So why we need the sequential circuits? So in the digital logic circuits, we have assumed that they perform their computations instantaneously, but it's not like that. They take some delay also. So our logic gates induce a small amount of delay also. So in order to get perfect them, we use the sequential circuits. And in this circuit, we can access the past data as well. So we use this. This is a useful. So as you can see, this is the combinational circuit. In this, we don't involve any of the previous outputs. So here we give some inputs and we obtain some outputs. But in this case, we give some inputs and we involve some previous outputs as well using some memory element. You will get to know about the memory element within few minutes. So, and this path is called as the feedback loop. So here is the main difference between combinational and sequential circuits. As you know, in the combinational circuits, output depends on the current input. Okay? And the sequential circuit, the output depends on the current input as well the previous outputs. No feedback loop. In the sequential circuit, we have no feedback loop. Here we have a feedback loop for the feeding of past. Is a made up of logic gates, and it's also involves some basic logic gates as well as the memory elements. There some examples are multiplexer, encoder, decoder, adder, comparator. We have seen all these in previous workshops. And the sequential circuits, we have counters, flip-flop, shift register. We will see about these in workshop. So sequential circuits are also various two types, but one is synchronous and the other one is asynchronous. The synchronous one, we use the circuit output changes only at some discrete point of time. Like we cannot change the outputs as we provide the inputs. We define some time interval in which we can change the output based on the set of instructions given as input. And the asynchronous one, the circuit output can change at any time. The example for this is latches, and the example for this one is flip-flops. We will study about the flip-flops and latches in the few minutes. So as we have discussed about the memory element, we feed the outputs, the memory elements. So what is the memory element? Memory elements are those circuits that can remember the value for some time and changes its stored value based on the input. So the memory elements are some elements which can store the outputs, previous outputs, and can change it based on the inputs we provide. So latches and flip-flops are the memory elements we use. And the latches operates with single label, hence they are called as the label sensitive devices. So why we call them as a single label? Why we call them as a label sensitive devices? Because they can change their values when we give them enable signal as 0 or 1. If we give 0, they will not change the value. They will keep output as a previous one only. When we give them as 1, they will change the output based on the input. And the flip-flops change their condition based on the clock signal. So about the clock signal, we will study here. So this is the clock signal. Clock signal is the square waveform. So this is we call here it starts from 0 and go to 1, and this is we called as positive S because it when it go from 0 to 1, so we call it as positive S, and this one we call it as negative S because it fall from 1 to 0, so we call it as negative edge. So as we have seen here, flip-flops change their condition based on the clock signal. So flip-flops change their condition in this region, in positive or negative edge. In this region, flip-flops will provide the output as the previous one only, and in this region, it will change the output based on the input. So triggering of the sequential circuit. So triggering means the changing or distributing the present state of the sequential circuit. So triggering means changing the output based on some present inputs or the past outputs. So we know the sequential circuits of feedback. The concept make it possible to have two possible states. Marked as a current state of the previous state, each sequential circuit can be characterized by the two states. So in this we call it as edge triggered circuit. This positive S and negative S. We call it as positive edge triggered circuit, and the level triggered in this region we call it as a level triggered circuit. So flip-flops are edge triggered and the latches are the level triggered. So types of triggers, level triggers and the edge triggers. So level triggers we have in level triggers we have 0 or 1. This is 0 and this is 1. So the circuit is on when it is in one region and the circuit is off when it is 0. What does it mean by on and off? So on refers to the thing when the output will change based on the input, and when the circuit is off, the present output will remain. The present output will remain as it is as the past output. So nothing will happen whatever you give the input. The example is latch, as I already told you, and the S triggered. S triggered is of two types: positive S triggered and the negative S triggered. So when the clock goes from 0 to 1, it is a positive edge trigger, and when it fall down from 1 to 0, it is negative edge trigger. So, the examples are flip-flops. So flip-flops can be of positive edge triggered as well as the negative edge trigger. So there are two types of flip-flop. See them. So now we will study about the latches. So this is a latch. So latch can be implemented using some gates. Here we are using the NOR gates. So this is the SR gate, S for set and R for reset. So this is it's a functional table, function table. So study about it. When we are giving it inputs as 1 and 0, we are getting Q as 1 and Q prime as 0. So here we get the output as Q and its complement as Q prime. So, and this is the NOR gate, as you can see. So let's say we are providing here and here is 0. As you know, when we in the NOR circuit, when we get when one of the input is 1, it does not depend on the other input. It gives the value as 0. So here, if here input is 1, here this 0 will go here. Now we have 1 and 0. So the output of this NOR gate will be depend on the 1 and 0. NOR gate will give, if we have 1 and 0, it will give 0. So here we are getting sorry, we have here I have explained this one. I have put an S is equal to 0 and R is equal to 1. We will get 0 and 1, and we call it as reset state. When the value of Q is 0, we call it as reset state. When the value of Q is 1, we call it as a set state. So in this case, if we have S as 1 and R as 0, Yes, if we have as 1 and R as 0, so we will get if in NOR gate it does not depend here. You can see it as if we have 0 and here 0 0 we will get 1. So here we will get Q as 1. Yes. Here will be Q as 1 and Q prime is 0. Call it as set state. And if we give if we give S and R is equals to 1, here if we give, we get it as 0 and 0. But as it is Q and Q complement, we cannot get this. So we define it, we call it as undefined. So this condition we cannot get, so we call it as undefined one. SR latch using the NAND gate. Here we are using the NOR gate. Now we will use the NAND gate. So this is a similar, but we just change the gates here. So if the S prime is 0 and R is 1, so in the as you know, in the AND gate, it does not matter if we have one input as 1, the output will be if we have in NAND gate, if the one input is 0, we will get output as 1. It does not depend on the other input. So this one will, and we have 1 and 1. So NOR gate means AND plus NOR. So 1 when AND is 1 and we will take it to NOR. So we will, here we are getting 1 and that state because is 1 and is. If we give 1 and 1, if we give it is 1 and 1, and here it will go as a, here it will go. So if we take NOR of the NAND of this 1 and Q, so how we take the NAND 1. So what we'll get 1 dot Q, we will so you, yes, we'll get 1. So here we will get as Q prime. So it will remain as the previous state only. We have given the Q, getting here the Q prime only. So the Q prime, like it will, the output will be the previous one. Whatever we were getting in the previous cycle, we will get this one only. So here we are getting 1 0. Here also it has the 1 0 only. And in this case, if we get the 1 and 0, we will give it. So it is a NAND gate. If you give input as 0, it does not depend on the other input. It will give as 1. 1 will go here and it will give as 0. Next one, if we have 1 and 1, the same thing will happen as in this case, and it will remain as the same state as 0 and 1. It will remain as it in the previous state. Previous output was 0 and 1, so it will remain as at 0 and 1. In if we give it as 0 and 0, we will get here 1 and 1, which is undefined. Here, in the case of when we are using the NOR gate, the undefined state was found when we are giving output as 1 and 1. And here, when the S prime and R prime is 0, it means the S and R are 1 and 1, then we are getting the undefined state. So when we keep the input S and R 1 and 1, we get the undefined state. So now we'll move over to the SR latch using the enable input. So here we give the one input as called enable. So when the enable input is 0 and it is the NAND gate, when the enable input is 0, it does not, when it is 0, it will not depend on the S and R. It will give 1, 1 and 1. So 1 and 1. And as you know, when we get 1 and 1, and the remaining thing is similar with the SR NAND using the NAND gate. And you know, when we get 1 and 1 in NAND gate, it gives the 1 and it remain as the previous one only. So here also it will remain as the previous one. No changes will occur. Whatever the input is at S and R, because it will not depend on the S and R. So that's what I was talking about in the latches. If we give enable as 0, it will not change the output. It will remain as it is the previous one. And when we give it as 1, we have S as 0. So 1 and 0 will go here. And 1 and 0 output will be 1 only. Is that also 1 and 0? If we give it as output 1 and 1, here in this case 1, 1, 1, was the remain as the previous one only, the previous case. Next case 1. Here it is 1 and 0, so it will be in the NAND gate. If we give 1 and 0, we get 1. If we give 1 and 1, so in this case 1 and 0. So as 1 and 0 we are getting 0, 1. But in this case, let's say Q is 0 and prime is 1. So this 1 will go here. 0 and 0 and 0, it will give 1, and 1 and 1, it will give 0. So we're getting Q is equal to 0. As I told you, when Q is 0, we call it as reset state. When Q is 1, we call it as set state. You can see this one this way also. Here it is 0. Here it is Q. Here. Yes, here it is Q. So take dot, and this will be the output of the AND gate. So here it is coming as Q. So Q and dot 0, it will be give 0, and prime of 0 will be 1. So Q prime will be 1. And here, if Q prime is 1, then Q will be 0. We're getting Q as 0. So in next case, our enable is 1 and S is, so if we get 1, 1, we give 1, 1, we get here 0. We get 1, 0. In this case, let's say Q prime, here we are giving Q. The output will be 0 dot the NAND gate. So the Q prime with the 0 will take the AND, it will give as Q prime only. And when we'll take the double prime, Q prime with 0 will take AND, it will give us the Q prime. And this is the bar of the whole, so it's a bar of the whole. And we, as you know, when we take the double bar, it will give the, sorry, when we take the AND with 0, it will give us 0. The bar will be 1. The Q will be 1 in this. It is the set state. Then it is 1 and 1. Then it is 1, 1. We will get here 0. Let's do this once again. If here have time, the output get here 0 time is equal to 1. Here you are getting Q is equal to 1. And if you do the same thing with this prime, here also we will get as 1. But we shouldn't get this. We should get the prime of Q, but we are getting as 1 and 1. So it is the undefined state for that. I've seen the SR latch using the enable input. Now we will see the D latch. So in SR latch, we have seen we can give the input as 1 and 1 both simultaneously, and 0 and 0 both simultaneously S and R. But in the D latch, we R is equals to S prime. We do not give the input as, we only give the one input. The other input is the complement of this. So in this case, if we are getting the 1 1, we was getting undefined output. But in this case, if we will not give the as an input as 1 and 1, so we can avoid this condition, avoid this the undefined condition. Enable, if the enable is 0, one input of the NAND gate is 0, we give 1 and 1. It does not depend on the D, whatever D, if the D is 0 or 1, it will not depend on this. This 1 and 1, this condition will, the state will remain the same as we have seen. Then 1 1 condition, it is equal as 1. So D is 0. So here the OR gate is the NOT gate, so it will be 1 here. And here input for this gate will be 1 and 1. The NAND gate 1 and 1 will give 0. Is 0, here it is case of 0 and 1 gives 1. This is a similar condition when in this case when we were giving 1 and 0, 1 and 0, we were giving 1 and 0, give one set state. Here let us solve this. So here it is 1 and 0. Here we will give the input as Q. What Q? Will 0, it will be 0. R of 0. So Q prime we are getting 1, so Q will be 1. Q prime we are getting 1, so Q will be 0. So Q will be 0, it's the reset state. If we give D as 1, so here we will get 0, and enable will 1 will be input this 1 and 0. 1 and 0 we get 1, 1 and 1 get 0, 0 1. Here the input will be, the output will be 0, and so q prime with will take the AND with 0, it will give q prime, and the whole bar it will change it. Q prime with 0 we will get 0, whole bar of 0 to 1. The set statement. One it is called as set statement gives set state. So here comes the JK latch. We have done B latch and a SAR latch, and we have done a SAR latch with the enable inputs, AND gate and NOR gate. The JK latch. The JK latch, we have an enable and we have JK, and bring back the output this NAND gate, this output to this NAND gate. Let's say if the enable is 0, the enable is 0, here with that one, here it will remain as the previous plate. It will, output will be the previous one, no change, there will be no change. We does not consider, it is not important. 0, the previous enable is 0, the output does not change, it the previous one only. That's why it is not later when the enable is 1 and have J as K as 0. This is NAND gate. If have one of the input as 0, whatever the other two input get here 1. Same with this one. So as we know, when feed in this 1 and 1, the output will not change, it will remain as the previous one. And it will remain the previous one Q0. We have J as 1, K as 0. Again, one of the input is 0, so we will get 1 here. And now it will dip. We have 1 and 1, and now it will depend what comes from here. In this case, it will depend in this case because we have 1 and 1. In this, so if one of the input is 0, is 1 1, we will get 0 0 1, and we will get, will be our 1 when we have 1 and 0 at the JK. You can see it as by solving this way also, as I have solved taking Q and Q bar. Other one, and similarly, if we have it, we get 1, and it will depend because we both the inputs are 1 and 1. Second, if we have 0, this will give 1. If we have 1, if we have 1, this will give 0. So it will depend on the third input of NAND gate. Here we have 1. 1 will go here. Here also 0 will go get 0. This 1 will go here, then we will get 0. This 0 will go getting to as and if we have j as 1 and k as 1, we will get the outputs as q naught. So we call it as a toggle. Toggle means the output will reverse. Output will be complement of the previous input. Output will be complement of the previous output. Toggling means the inverting of the output. So we can see it will depend on this one. It will in both the cases it will depend on solve this and we'll get the q naught. So now we'll study about the flip-flops we have done with the latches, and as you have seen, latches work when the enable is 1. When the enable is 0, the outputs will not change. Output will remain as the previous one. When the enable is 1, the output will be behave as we give the inputs. It will depend on the inputs. So here the flip-flops. So as we have seen, the flip-flops are the latches are the trigger. So the flip-flops are the triggered input. So flip in the flip we will see the change in flip-flop output when the clock, as we have seen here, the clock, when the clock is going from 0 to 1 or 1 to 0, then only we will see the change in the output of the flip-flops. So there are some problem with the latches. So we use the flip-flops. The latches cause some synchronization problem. So we use the flip-flops. So we have various types of flip-flops: T flip-flop, JK flip-flop, D flip-flop, and SR flip-flop. So we study about these types of flip-flop. So as we have seen, we have two types of edge triggering: positive edge triggered and the negative edge triggered. This one is a positive edge triggered. This one, the left side one, the negative. So we have two types of flip-flops. One is positive edge triggered and the negative one triggered, negative level triggered. So the circuit for the SR flip-flop, it will be same as the latches, but here it will be same as the latches, but here in give here the clock will be provided and the output will be changed when the clock will go from 0 to 1 and 1 to 0. When it is in the same label, like when it is on 0 or 1, the output will not change. So we denote clock as this arrow. So this is the positive as triggered, and when this negative is triggered, we put a bubble over here. This is the negative as triggered. This is positive as triggered. The inputs. So X, it means whatever the clock is, if the input of SR is 0, 0, there will be no changes in the output. The state will be the previous one, or like the output will be the previous one, previous output. And when the clock is this shows the clock is going from 0 to 1. When the clock is going 0 to 1, from 0 to 1, the output will behave according to the input. So here will be 0 when the output will be 0, as we have seen in the SR latch also. Similarly, it will behave. But the main difference is the output will change when the clock is going from 0 to 1. The same we have seen when SR is 1, 1, it is a forbidden state. Here it is a D flip-flop, as we have seen the D latch also. It is a D flip-flop. It is the positive as triggered and it is the negative as triggered. So when D is 0, and the state will be reset, and when D is 1, note that it will be when the clock is going from 0 to 1 or 1 to 0. We are based on the which type of flip-flop we are using, positive as trigger or the negative. If we are using positive as trigger, the clock is going from 0 to 1, then we will get this output. If the negative as triggered, the clock is going from 1 to 0, then we will get this output. corresponds to JK flip-flop. Similarly, outputs will be the same as the latches, but here also when the clock in case of positive is triggered, when the clock will go from 0 to 1, we will get this type of output. And in the negative is triggered, when the clock will go from 1 to 0. So here we have a T flip-flops. T means the toggle flip-flop that it invert the outputs. When the T is 0, the output will remain as the previous one. When T is 1, the output will invert. So when T is 0, the output will remain as the previous output. And T is 1, the output will be the complement of the previous output. In this circuit, we use the NAND gate as well as some OR gate, I guess. We will give some material. So one example based on this T flip-flop. So as you know, when we keep 0, the output will remain same. When we keep 1, the output will invert. Here's the example for you. You can solve. If so, here we have two flip-flops, two T flip-flops. Here it is clock. Here it is 1. T is 1, and the output of this flip-flop is given it as clock to this flip-flop. We'll wait for a few minutes. You can try it. So I can give some hint. Like you should see the clock in this case. So here it is given as Q1 and Q0 is 0, 0. So previous output is 0, 0 for both the cases. So here it is here it is initially we are giving 1. T is always 1. Okay. So you can see when T is 1 what will happen with this output. We are and same T is going here also. So here also T is always 1. So you can see what will happen with this, but you should remember we are giving this input as a clock in this. So this will only change when clock is in triggered region and it is a positive triggered flip-flop.
हेलो सो हो गया समय
एग्जांपल सॉल्व करें तो
अच्छा अच्छा ओके
if one is getting, they can speak or you can write in the chat box also. I will show you the question. So the question, we have the options. You can say which option is. Anybody getting, or we should move? If anyone is solving, they can raise their hand. Raise your hand, we will wait. Otherwise, we will move forward. Wait, if anybody is solving, they can raise their hand. Otherwise, we'll move forward. Okay, so we'll solve this. So, as we know, okay. So here the t is always 1 and the previous input of previous value, the previous value for q naught was 0. Previous value for q naught is 0. And t is, as t is always 1, so when t is 1, the output will invert. So output will become 1, then 0, 1. So this is the value of q naught. But this q naught is going in this as a the clock signal. So and in this case also the t is always 1. So 1, initial value of q1 was 0. So it will become 1. But in the second step we have to see the clock. So this was the clock. This clock is going from 1 to 0. So the clock is going from 1 to 0 and this is the positive triggered one. So but 1 to 0 the clock is going from 1 to 0, but so the value will not change, it will remain as 1 only. Because the positive triggered one change the value when the clock is going from 0 to 1. It will remain as it is. And the third step, clock is going from 0 to 1. Will change the value as t is 1, so it will invert the value as 0. And the fourth step, the clock is going from 1 to 0. So it will not change its value, so it's 0. So we have to give answer as q1 and 0. So q1 is our 1, 1, 1, 0. So answer will be 1, 1, 0, 1, 0, 1, 0, 0. The answer will be, can solve. We will provide some problems also based on that. So yes, Sandeepan, you can take over. Sandeepan?
Yep. Yep. Can stop sharing. Also, guys, before moving forward, I would like to say one thing. Whatever Soumya has covered today, whatever we have covered in the previous two workshops, and whatever we'll be covering in future, and the workshop is not over yet. Okay, I'm going to still take a part two, so don't leave, guys. At the end, we have a demo, and I'll also be showing how to install Proteus. So whatever we have covered so far, and we'll be covering all that is there on your YouTube channel called Nesa Academy. You can just Google it up, Nesa Academy Digital Electronics Course. Okay, and there's a playlist of around I don't remember exact how many videos are there, but whatever we have taught and we will be teaching, everything is covered there in detail. Okay, so you can always refer back to that if you don't understand anything that we're teaching. Okay, and so continuing on, one sec. Yeah, so coming to asynchronous set and reset. Now, each flip-flop that Swami has shown you so far, they have two extra pins. Okay, one is S and R. What they do is, like initially when you have a hardware flip-flop, when you have a real flip-flop, when you power it on, you don't know the outputs, right? It's random. Sometimes you can have 0, sometimes you can have 1. So to set it to some specific value, there are two pins. Like one is S, one is R. If you give 1 in S, right, digital logic 1 in S, then Q becomes 0. So that is called, and then Q becomes 1. That is called set. Okay. When Q becomes 1, it's called set. And when you put 1 in S, Q becomes 1. And similarly, to start flip-flop with an output 0, you have a pin called R. When we give 1 to R, then the output is 0. Q becomes 0, right? So, but the special feature of this thing is that this change does not happen with the clock. It happens asynchronously, means it's a combinational logic, right? It doesn't have the, you give s equal to 0, you give s equal to 1 or r equal to 1, instantaneously the output will change at q. Okay, it will become 0, it will become 1 as depending on which pin you're giving the input in, right? So that's why it's called asynchronous, because it's not synced with the clock. Now moving on, you have to now coming to the how do you make a flip from a latch? For that you have a configuration called master slave, right? How do you convert a level triggering to an edge triggering? So basically it's this easy to convert that to make that happen. You just connect two latches in series, okay, and just invert the clocks. If I go back to a D flip flop, to a D latch, right? If I have the same exact replica ahead of this again, and if I just toggle, give the knot of enable, right? If I just do, this, right? If I just invert it and I give this as the enable of the exact same thing ahead again, then I get a flip flop. I get a D flip flop. Okay. So, and here the first latch is called the master latch. The second one is called the slave latch. So what happens is when you're giving it a D, say let's say D is one here. I'll just demonstrate using. So this is my clock pulse. Okay. Say this is my clock pulse. Now say I'm giving DS1. Okay. I'm giving DS1. So let this be the output, Q1 be the output of the first latch, and Q2 be the output of the second latch. Okay. So what will so now my D is 1. Okay, all the time. So once yeah. So when my this part is high, right? So at the latch, this is level trigger, right? So the first Q1 will become 1 here itself, right? It will become 1 here itself, and it will remain 1 till the end. Why? Because if you notice, during the first half of the clock, this is enabled, right? Then during that time, this one is disabled. So during the first, when the clock is high, right? The master latch is on and the slave latch is off. And when the clock is low, then the master latch becomes low and the slave latch becomes high. So what happens is, following that, Q2 becomes high here when this is low, right? Because this one reaches the slave latch, then this becomes D, right, for the slave latch. And at that time, the clock for that latch is high because I'm feeding the inverse of this. So then Q2 becomes high there. So what do you get here? You notice that when the clock negative edge happens, right? This is a negative edge. At that moment, my output becomes 1 here, right? Now you might think that why do we need this exactly? We'll be coming to that soon. Why? I mean, what is the shortcoming in a latch that we had to make it a flip flop? We'll be coming to that soon because yeah, so this is why we need it. When you have a JK flip flop, what happens is for a single level, when you have a JK flip flop, right? Again, you have the clock. What happens when a JK flip flop? We put in J and K as 1, right? What happens when you put J and K as 1? The output inverts, right? So what will happen is the output is 0. Let Q initially be 0. Now I give it as 1. Okay. Now when the clock is high, this entire duration of time, my latch is enabled. So what will happen is it will become 1, it will become 0 again, 1 again, 0 again, infinite number. I mean, a lot of number of times. Can't even count, it will be so fast. Like during the single clock cycle, it can toggle as many as 1,000 times, 10,000 times. You won't even know, right? And again, the same thing will happen here, and so on and so forth. So what will happen is you cannot predict what will happen, the result, the final output that will be after this has happened, right? You cannot say finally whether it is just 0 or it is 1. So for that, you make this toggling. This is called this condition is called trace around condition because it happens a lot of times during a single clock. So for this exact reason, you make flip flops. So that for a single change in the so that the output changes only on the edges. The same thing you can notice here. And this happens because if you notice in the D flip flop, in the D latch, there was no direct connection between the output and the input, right? This thing was not there. This connection between Q and J, right? But here we have that. That is why this the race around condition occurs here. Q bar is fed to J and Q is fed to K, right? If you notice again, these are two JK flip flops just connected together. The output of this feeds into this, and the rest everything is same as that of a latch. Now the easiest way to analyze this is this thing. Let just imagine J and K is 1. Okay. Let Q be 0. Q be 0. 1 second. Yeah, let initially my initial state be q equal to 0. Cool. And q bar is 1, obviously. What happens is now, if you look at j, what's coming at j? Let my clock be high. Okay, clock be high. So 1 at clock, j is also 1, and so is my q bar, right? So the output of this is 0. Cool. And the output of this is 0, right? 0. So 0 become automatically this becomes 1, right? Since q is 0, automatically this becomes 1. So I have 0 and 1 here. Now since I have 0 here, the output of this NAND gate, and this is the best way to analyze it. Just look at the 0 right here. So my m becomes 1 instantaneously, and this is m bar, so it obviously becomes 0, right? So I have 1 here and I have 0 there. Again, I have 1 here and I have 0 here. So if I have 0 here, then this becomes 1, right? And this one, the clock here is also 1. So 1 and 1. Here I am getting a 0. And so if I'm getting a 0 here, that means again the q becomes 1. That's exactly how I analyze these circuits, right? And so q becomes 1. So initially it was 0 1, and now it is 1 0. During a single clock cycle. In the positive half, I'm getting 1 0 here, and in the second and the negative half of the clock cycle, I will get final output as toggled 1 0. Cool. So coming to flip-flop conversions. Now all the flip-flops you said ahead, SR flip-flop, D flip-flop, T flip-flop, and JK flip-flop, they can be interconverted, right? Uh, because everything is same in them. They all have feedback elements, and all they're pretty similar to each other, right? So you can easily convert them using just combinational logic. Okay, nothing more. So what are the steps to do that? Number one, like say if you don't have a T flip-flop but you have a JK flip-flop and you want to implement a T flip-flop from a JK flip-flop, right? So how will you do that? So step number one, you take the characteristic table of the desired flip-flop. And how to do that? I mean, and what is the characteristic table? I'll be showing you that with an example. Then you check in the fill-in values, the excitation values of the flip-flop. I guess I'll move to the example. It will be easier for you to understand. Come on. So we are converting a D flip-flop to a T flip-flop. So that means that we have been given a D flip-flop and we have a D flip-flop with us, और हमें बनाना एक simple T flip-flop, right? So step number one, draw the characteristic table of the T flip-flop. Now this is exactly what I mean by characteristic table. You have the input T, you have the present state, and you can predict, like this is the input part and this is the output part. You can predict the next state of the T flip-flop. So if I'm having 0 0, yeah, I guess I saw myself to this. So for 1 0 to toggle, so that's all it says. Now step 2 is you add the excitation table for the D flip-flop here, and this is what I mean by excitation table. Just appending it, this part to this column, I'm appending to that part. And what is this? How do you write this column? The rest is same, right, from the previous one. But how do you write this column? You put in D. You check QT changes from 0 to 0, right? QT1, QT plus 1, right? So what should be my D for that? If I had a D flip-flop, imagine for the state to change from 0 to 0, what should have been my D? My D should have been 0, right? Obviously. Now again, if my QT is 1 and QT plus 1 is 1 again, then what should be my D? It should be 1, because whatever the input is, QT plus 1 becomes equal to D, right? As we studied in D flip-flop. So same here. If I had 0 and the next state is 1, again I'll have a 1 for D as input. And this is exactly how you make this table. And this is called an excitation table. So once you have this entire table, you come to step 3. Step 3 is find D as a function of T and QT. So ignore this column now. Just look at these first column, second column, and the last column. Let it be like A and let this be B, right? And this is my output column, O. So I have to find O as a function of X and Y. And how to do that? Using a simple K-map, right? Just take T and QT and put in the 4 values here. And I can see D is 1 for 1 and 2, right? So for 1 and 2, D is 1. And as you can see, there is no simplification possible here for K-map. So if you write it down, you get TQT bar plus T bar QT, which is equal to T XOR QT, right? So we got D as T plus Q XOR, D as T XOR QT. And coming to the last and final part, the circuit. So we had a D flip-flop, right? And this is my D input going to it. And how do I make it a T flip-flop? I just do a XOR of QT and my input T, right? So then this entire red box becomes my T flip-flop. So that's exactly how you can see how easy it is to convert a D flip-flop to T flip-flop, right? And the same using similar techniques, you can also convert D to JK, JK to T, and there are 12 combinations, right, in total. So you can convert any one to each. So we'll be giving an assignment where maybe we'll put 2 examples for you to try out by yourself. Okay, within a few days. Now coming to registers. So we have studied in sequential logic, we have studied latches, we have studied flip-flops. There are 2 things left. One is register and one is counter. So counters will be covering in the next workshop, but in the last thing in this workshop is registers. To increase the storage capacity in terms of bits, right, we have a group of flip-flops. A flip-flop can store 1 bit, right? I put in D, it stores that in the next cycle. But what if I have n bits? What if I have a 4-bit number? I don't want to use 4 individual flip-flops. I want it to be a single integrated circuit, right? So that exactly is what a register is. So it's a group of flip-flops. That's it. I won't be explaining more. Rest you can understand in the demo. So an n-bit register can obviously store an n-bit number. So there are some registers that allow the shifting of data within itself, right? If you have 4 flip-flops connected in series like this, you can shift data from left to right, from right to left, right? So there are 4 modes of operation of a shift register. They are called shift registers. Number 1, we have serial input, serial output. Number 2, serial input, parallel output, and 2 more examples in the same way. So the first diagram we can see here is serial input, serial output. What happens is, say imagine you have a sensor that is sending you values, right? Like 0, 1, 1, 0, or a binary number. You are sending the bits one by one into this register. Okay. Say imagine you have 0, 1, 1, 0. So the first you have 0, 1, 1, 0 maybe. Okay. You're putting in 0 as your input here. That is called a serial input, right? And your output is the final value here. So, and let initially the flip-flop be this be 0, this also be 0, this be 0, this also be 0. Okay. So the first input is 0, right? In the first clock cycle, I'm putting in 0. And my output is 0, right? This is my output, the value at this register. The next cycle, I'm putting in 1, right? So my 1 enters in this way. So now my output of the registers is 1, 0, 0, 0. How does this happen? 1 comes here, whatever was here gets shifted there, whatever was here gets shifted there, and so on and so forth. In the next cycle, I'll have another 1. So now I'll be having 1, 1, 0, 0, right? And then last I will have another 0, so I'll be having 0, 1, 1, 0. So this is serial input, serial output, right? Now coming to serial input and parallel output. Nothing, the same thing exactly. Instead of looking at the last output, my output is this entire thing, all the 4 bits together. That becomes a parallel output. As you can see here, this is the parallel output that you're getting. Then coming to PIPO, should be input. Yeah, so you are putting in 4 values simultaneously. Instead of feeding in at one end, you're feeding it at all the registers, at all the flip-flops, right? And what you're getting is, again, the output is parallel, meaning you're looking at all the bits at once. So just you can think of it like you're storing a 4-digit number, a 4-bit number. So putting in a 4-bit number, the output is also a 4-bit number after one cycle. So basically storing that number. And the last mode is PISO, that is parallel input and shift output, parallel input and serial output, right? This is a good example of the above 2 circuits put together. If you notice, these 2 have been put together, and this one has been made, right? So if you see, there are 2 functionalities here. One is parallel inputs, all like B0, B1, B2, B3, and the serial input that is coming in here, right? This is connected to this, like in the previous one. I mean, the serial one, as well as this is connected to this, right? This is connected to this as well. And how is this done? One second, let's clear this out. And if you see, it is very no, it's easy sequential logic. You have one extra line which tells you whether to shift data or to load data, right? Which comes into this one. So if you're shifting data, just multiply this with 1, and that value is fed into this. It becomes OR and it's fed into this. If you just do some simple calculations, you will see that this is what is happening. right? When shift is 1, the values get shifted. When load is 1, the values get whatever is at the input, whatever is at the input, this value comes out as the output. Okay, and when so that is it, I guess, for this part. Now coming to the last, the god of registers. And this is what we'll be using for your PS also. It's the universal shift register, right? What this can do is the exact same thing here, right? But there's just one extra feature, that is this shifts only right. This register can also shift left. Everything else is same. So this had one input line, right? Shift or load. So one input line. This has now, since there are 4 things you can do it: shift right, shift left, parallel load, and no change. So there are 2 select lines. Okay. So there are 2 select lines here. I guess I'll zoom in on this. Yeah. So there are 2 select lines here. So if you notice, the circuit may look quite complicated, but it will take you just 2 minutes to understand. Say I'm feeding in 0 0. Okay. So S0 S1 feeds to these are muxes, right? These are multiplexes. I hope you remember what multiplexes are, right? We have 4 inputs, and but the output will be only 1. From the previous workshop, I think we have covered it. So when both are 0, the first input comes in, right? And these are the flip flops. Okay. So when both are 0, the first whatever is connected, you see the output connected here comes in back. That is no change for each of them. That means there's no change, right? Now, if the output is fed into the rest of 1 second, whatever is there still remains there, right? Now you're having 0 1. That is right shift. How if you think how it's right shifting, then if you look at it, 0 1 means the whatever is coming here will get selected, right? So 1. So right shift means the shifting to the right. So whatever input I'm giving here, so this is a separate input, right? It's called SI, right? This has the bit which is supposed to come in from the left. So this comes in left, right? This gets in here, becomes the output of this flip flop. Whatever was stored here goes into this. If you notice, it's connected to this one, right? It comes here, this comes in and to this one, and like that the values get out. And this is my final output which comes out here. Serial output for out. This is my output, right? Going back, the exact same thing for left shift when I'm putting in 1 0. So notice not connected the reverse way around. Like here I'm putting in my input here, right? My output goes here, goes here, goes here. Same, it goes here for 2. So the output of this comes here and 2, like that. It feeds to the previous mux and the previous flip flop eventually, right? And the last mode you can have is parallel load. In that, it's very easy. Nothing happens. Simply whatever is at 3. This is 3, right? So 3, this will get selected. So whatever comes in here, this feeds into this and just have the output as coming out simply parallelly, right? These 4 are parallel outputs. So that is for universal shift register. I guess you're pretty much bored of this theory now. Maybe you can have a look at the implementation on Proteus, right? So it's time for a demo, but first you have to install Proteus 7.8. For the event, we are supporting Proteus 7.8, right? But you can also use Proteus 8. There's no restriction as such, but Proteus 7.8 is just preferred. You can still use anything else you want, and this is the link. You can just go on to this and download it. This link is also there on the teams under the file section under the Digisim team, right? You can find this link in a text file. So you can go ahead download it now also, but I guess we should wait for the demonstration now, right? So coming to the demo, yeah. So on the one I start. First maybe you can look at the clock, right? So welcome to Proteus. Maybe some of you have seen it before in other workshops for Xavata and everything, but for like I'll be introducing you to Proteus here as well again. So this is a sheet, right? Everything is put inside this blue box, and this is the play button which simulates to start the simulation, and the stop button which ends it. So I have a clock here. I'll show you how you can add your own clocks and everything, but first I want to show you what all that we talked about today, right? So this clock that I have here, I've been plotting the clock on this graph here, right? So if you look at this graph here, you can see the clock waveform. If you notice, the time period is 2 seconds. Corresponding to this entire part, you have 2 seconds. And that is because okay, I'll come to that later. So that is the clock for you. And this is a simple D flip-flop. 7474 is the name of the flip-flop. So what happens is, I'm putting D as 0, right? I'm putting D in a 0 here. And so my output is 0, right? The moment I change it to 1, uh, the moment I change it to 1 here, my output becomes 1, right? The again you can see the clock blinking orange and blue, right? Orange is high and blue is ground, right? So if I make it 0, you will notice at the next immediate tick, at the next immediate orange line, it will become 0. So that is a D flip flop. Now coming to a JK flip flop. Okay, now you might be wondering that, as I said, that for JK flip flop, when both the J and K are 1, the output should toggle, right? Right? But why is it not happening here? Because of this guy. If you notice there is a circle before K, right? That means that the whatever is going in the not of that is fed to that input, right? So basically, my JK is 1 0 here. Okay. So if I make it 1 0, now it becomes 1 1, and you see my output will toggle 1 0, it becomes 0 1 again, like that. Okay. And so if I make J as 1 and K as 0, so obviously my output should be set, right? Should always remain 1 0. If I make J as 0 and K as 1, then it should always be 1, right? Q bar should be 1, Q should be 0, and toggling I've already showed you. So that is for D and JK flip flop. Coming to this is a shift register. Now it is not a universal shift register. It is a normal shift register. Why? Because it can only shift right. It cannot shift left. So as you can see, there are two pins here, right? One for shift, one for load. So initially, now I'm having a shift as 0, right? And load as 1. That means I'll be loading whatever comes in parallel input will become a parallel output, right? So if you look at this number, this is what 0 in binary, right? This is 2, right? If I'm making this as the MSB and this is the LSB, then this is 2, right? So you see whatever is here will come in there now after the first clock cycle. It will stay there because I'm not changing anything. If I change this to 6, then become 6, right? Now, if I'm not loading, if I'm shifting, say I'll make shift load as 0. When both are 0, nothing happens, right? Now when I make shift as 1, you see my serial input here is 1, right? So 1 should start getting it from this side, and we'll start pushing down all the other values to the bottom. So time to make shift 1 there. Another one will get in now. Another one will get in, and it will push out everything, and the output will eventually become all ones. Now if I make this 0, then 0 will get in from there. Yeah. So that is all about my shift register. Now a universal shift register. Now this has 2 pins, right? One is serial input right, and one is serial input left, right? Because here at one input from this side, I'll also have another input from this side now. Cool. So configuration 1, when both are 0, right? Nothing should change, and nothing has changed yet. There is no change absolutely, right? Initially my output was 0 of the circuit, and it still remains 0. Even this hasn't loaded out because both are 0 here. Now if I make say both as 1, if I make both as 1 means that it will toggle, right? It will load this value inside, right? So there, the value comes loaded there. Yeah. So let this be. And now if I make it 0 1, then whatever is connected here through serial left to right that you can figure out for yourself, that will start pushing it from one side. Okay, so I had 0 connected here, right? And 0 is getting inside. If I make this 1, okay, this one is shifting right actually. So 1 is coming inside. So bottom is right. Okay. And if I now make this 1 0, then yeah, it's going up back again, right? And it's going in zeros because zeros are getting from the left. right? If I put in 1, then 1 will start going in from this side. Now, if you're wondering that what these other values are, like MR, here also you had MR, and you might have any IC where there are these additional pins, right? For which values you don't know what to put in. So you can notice see the number here 74194, right? You can just Google search up this IC and just search 74194 data sheet. So you get a detailed pin diagram and of what all the pins do and what you should be giving to the pins to get the correct output. Okay. So that is what you should be always referring to if you have any doubts as to what you should be connecting to some pin. What is this circuit? This is an octal flip-flop, right? So one flip-flop, again 8 consecutive flip-flops. I mean, make it an octal flip-flop, right? But it's not a register. Okay, don't confuse this with a register. If you notice the difference between them, it's nothing but a register has shift and a load line, right? But this does not have anything like that. This just whatever comes in as the input becomes the output in the next part, right? It's a D octal flip-flop. On the clock, once the clock triggers, the input becomes the output, right? That's all that happens here. There's nothing about shifting, nothing about nothing about shifting. That's it. So that's it. You do not have any control. Whatever comes in here will become the output unless and until you disable the clock, right? Like here, you could have made load as 0, right? And you could have stopped feeding into this. But here, whatever comes in as the input will become the output unless and until you make the clock as 0. You disable the clock basically. So that's the fundamental difference between the resistor and octal flip-flop. Now coming to something from the last workshop, it's a simple adder, right? A very simple adder that we're having here. So see 6 plus what is this? 4, 10. 10 becomes this, and if we're giving this, we have a carry output of 1 and 2 here. So it's a 5-bit number. So 4 numbers feeding into the first, 4 to the second, 4-bit inputs too, and we're getting a 5-bit output, right? As simple as that. And this is a simple multiplexer. Okay. I'll just make this as 2. Now for a multiplexer, if you remember, okay, can someone tell me what type of multiplexer this is? A 2x1 mux, a 4x1 mux, or an 8x1 mux? Anyone? Where's unmute your mic and say what type of mux is this? 2x1 mux, 4x1 mux, 8x1 mux? No one? Okay, so this was actually very easy, but this is a 2x1 mux, right? There are 2 4-bit inputs, and out of them only one will go to the output. As you can see, this is a select line, right? If I'm having 0, that means A bar. That means this one. The first input is A, right? 1A, 2A. So this is A. This becomes output. If I make it as 1, now output becomes B, right? As easy as that. The level pin just makes it. It's switch on and off, right? You can say for the IC. If it is like say if it is 1, then whatever the input, the output will always be 0. Okay, that is all. And the last thing that I want to show you is the comparator, right? So if you see again, there are 2 4-bit numbers. And this basically compares between them. A less than B equal to B A less than B, right? These are my 3 outputs. So in this case, you see that A is 1 and B 0. So my output is A greater than B, which is 1, right? If I do this, then my A is less than B, obviously. And if I make them equal, then A equal to B becomes 1. So these are all that we'll be using in order to solve a PS, right? Whatever you see on the screen here, these ICs are exactly what we'll be using to solve a PS. There also will be a counter that we'll cover in the next workshop. Other than that, I guess we are done here. Okay, also I had to show you some of the things on Proteus, that how do you start with your own circuits, right? So coming to that, I'll open a new file and show you. I'll just make a new design, just to make it as default, and start with OK, right? That's how you start. Now to select your own components, you click on this pick button, right? And maybe the first thing you might say, I want an adder. Let's type an adder here. Go to the TTL 74 series, right? For the entire event, we'll be using this series only, right? and all with TTL. Now, we won't be using CMOS or any other things. Whatever starts with 7 port, you can use that. Okay, we'll be giving you a specific list of ICs that you can use in the PS itself. So if you see, you have these options. So I'll be using this one, 7488283, and just click on OK, and it comes up here. Just click on the screen, and you have it. Double click, and you have it on the screen. Right. So this is the IC that I was showing you. Now, how do you put in those zeros and ones that I was showing you? Just pick again, go to type in logic state. So yeah, you see two things there. One is logic state. So first I click on that. Okay, and again I place it, and you can see I can place as many as I want. Right. Now if I want to see the output, how do I see the output? I light logic probe. So you can put these anywhere, and you can use this to test your circuits. Right. You can use them to debug your circuits. Just connect them. You can start playing with this by yourself, right? Once you can download it. So that's it. Basically, I guess you can see what happens here. So these two inputs are 0, so that's why it becomes 1. So let's put in the yeah. So that is as easy as that. You can put in zeros and ones there. What else? So if you want to use a maybe say a register, we have a lot of options. Coming to this, you have 74179. Right, this is what we'll be using. So why I want to show you this is that you can right click on this, right, and click edit properties, and you can set the initial value of this register. It may be 1, or you can put anything you want, right? Because the output is 4, so you can put in 255 as well. Sorry, you can even put in 16, I mean 15, right? And if you connect, then initially you'll see the output is all ones, right? Orange is 1, that is 15, right? Yeah, the next thing that comes, you have the clock. So the clock you can find by under this section, this sine wave section, right? You have D clock, right? Right click on it, and these are the properties. You can set the frequency, the time period, whatever you wish. I can put in time period to be 2 seconds. Okay. And I just connect this clock to this clock here, and there I have the clock. If you want to see how this, I mean the pattern of the clock, then if you want to graph it out, then just go under this part, virtual instruments mode, right? You can use a maybe, okay, go under the graph part. Under the graph part, you have the digital graph, right? Just drag and draw this. Right click on it, edit, add traces, right? Then, okay, as you can see right now, okay, you can add this U2 clock, right? So the name of this clock was U2 clock. So Proteus labels gives everything a name by itself, right? So every component here you see has a name. Other than logic states and logic probes, every component that you see has a name, like 74283, 74179. The name of this is U1, this name is U2, this name is U2 clock, right? So I just added that trace to this clock, and now if I simulate, right, I right click on this and do simulate graph. Then I maximize. Okay, it's 0. Why is that? Because the time ranges from 0 to 1, but in the clock time period is 2 seconds, right? So I'll just edit properties and make the stop time as 10. Right. I have to play again and then simulate graph. And if I maximize now, then I have the entire clock cycle, right? You can see in 2 seconds it's toggling. Okay, so that is about the clock graphs. Shown you. Anything else is left? Yeah. The next part is say, like for a circuit, we'll be using only one clock, right? Your entire circuit will be having one clock or the max 2 clocks, but there can be many components which will be having the same clock. Like say if I'm putting, maybe I'm putting 5 registers, right? So connecting the same clock to different registers, there can be 5, there can be 10, there can be 20 registers you're having. So it becomes very messy, right? So what you do is you put in a thing called a label. Okay, go to variable section, just click on this wire anywhere you want. Okay, and just type in, say maybe I'll give it a name of clock. Okay, so this wire has a label of clock. I can just make a dummy wire here and click on this. You can say small cross whenever on the cursor, whenever this label mode is selected, and you can just type in the name of the label that you want it to be, right? So this clock becomes the value here becomes value here as well, right? And it looks so much cleaner if you notice, right? So to see this clock here, it's also feeding in 0101, you can see, right? So that's one trick. I guess that's it for today. There are a few more tricks that I will show you the next time we meet, the next workshop, and we'll be finishing up counters with that. Okay, so I will be sharing with you this file and the presentation, and for the rest you can refer to NSO Academy for all the tutorials. I guess that's it today.